DC motors are great if you want to operate a motor continuously, so you have this continuous rotation and torque applied, for example. If you're more interested in a position-based application, one alternative would be a stepper motor. There are multiple types of stepper motors, including permanent magnet, or PM stepper motors, and that's primarily the kind that we will talk about in this video. There's also things like variable reluctance, or VR, and then there's hybrid stepper motors. Right? But our focus will definitely be on this permanent magnet type of stepper motor. So as we mentioned, these stepper motors allow us to get discrete steps in our actuation. So I can move from here to here in a particularly defined way. I don't necessarily need a sensor like we would have on a servo motor with a DC motor. Right? This is built into the structure of the motor. And the way this works is I have a rotor, and that rotor is going to have some poles associated with it. In this case, I've drawn one pole right here. And then I'm going to have coils on the stator, right? And these are hooked together such that this would be A and A prime. So the kind of circuit equivalent of that is I'd have A and A prime connected together in series right here. So I have a single current basically going through both of these coils together. And I have multiple of these poles on the stator. So if I were to draw or we often call them phases as well, if I were to draw a two-phase permanent magnet stepper motor, so in this case I have B and B prime, and I have my equivalent circuit over here. So this fixed thing right here is going to be my stator. That's what's going to have the stator coils on it, and the number of stator pole and coil pairs, so that would be like A and A prime, B and B prime. In this case I have two of those, is going to be the number of phases in my motor. So in this case I have a two-phase stepper motor. Right? If I also had a C and a C prime and a D and a D prime, then I'd have a four-phase stepper motor. Now, and the basic idea behind this is that I'm going to run a current through these coils such that I set up these poles. For A, I would have a south pole. For A prime, I'm creating this kind of north pole, and my rotor will then line up with these coils or these poles on my stator. Let's go through the basic operation of how this motor would rotate around. Right, so I'm going to have a current going through those A coils, through A and A prime, such that I'm going from A to A prime, and that is going to, these coils are designed such that that will give me a south pole on the A stator pole, and on the A prime I'll get a north pole right here. So effectively here I have a south right here and a north right here. And what that's going to do is that's going to create it's going to make sure that the rotor, and I'm going to use a single pole on the rotor, so a north-south effectively on the rotor, that's going to line up in this direction. I'm going to draw an arrow here also indicating that, so we can see how that changes over time. I should also mention that, when I have current going through this A coil, I have zero current going through my B coils. There's nothing going through the B coils. So that was my first step up here. My second step is that I'm going to now have current going through my B coils, and I'm going to have this set up from B to B prime, such that B is now my south pole and B prime is now my north pole on the stator, and I have no current going through the A coils. And so once I've done that, so now I've effectively created my north on the B prime, my south on B, and so that rotor is going to rotate to line up properly with that. So now I have north-south right here. I drew my arrow pointing to the north. So now I've rotated like this, right? This whole rotor has rotated in this direction. 1 step. So for step 3 here, I'm going to now have my current going backwards through those A coils. So I have a current going through A, but now it's going from A prime direction to the A direction. So A prime is now my south pole, A is now my north pole. I of course have 0 current going through, that's 0 amps going through my B coil right here. And so this is going to set up, in this case, a north right here, south right here, and I've moved from my north pointing toward B here to my north pointing toward A prime right here. So it's rotated again another step. And the 4th step here, I'm going to have B current, and I've rotated again in this clockwise direction. So for this particular motor, I have 2 phases. I have 1 pole on the rotor, right? And there are only 4 steps here, so each step is 90 degrees. So I can position my motor, or my rotor of the motor, at 90-degree increments along here with this particular motor design. So obviously the number of steps that I might have is going to really determine the kind of performance metrics I'd be interested in for a stepper motor. To calculate that, I'm going to define P as my number of phases in the motor and N poles as the number of magnetic poles on the rotor. And so my steps per revolution, I'm going to define as S. It's going to be 2 times P times that N poles. Right? And this 2 times P is effectively the number of stator coils. So let's look at a far more complex example than I previously showed you with that 2-phase motor. In this case, I have 4 pairs of stator coils, 8 total coils there. So I have a 4-phase motor in this case, so my P is going to be 4. I also have, in this case, 3 different poles on my rotor. Right, so 3 different pairs of these north-south poles. So in this case, N poles here is going to be 3. So the number of steps total that I get in my stepper motor right here, S is going to be 2 times number of phases, 4 times 3, the number of poles on the rotor. So in this case, it's going to be 24 steps per revolution. And if I'm interested in the number of degrees per step, right, I'm going to take 360 degrees, divide that by S to get the number of degrees per step. So 360 degrees divided by 24 is going to get me 15 degrees per step. Right, so it's still a lot better than the previous example that we did when we had 2 phases and 1 pole on the rotor, in which case we got 90 degrees per step, or 4 steps per revolution. Right? But depending on what you're trying to do, it still might not be great, right? So these are definitely a little bit limited in terms of the kind of angular position that you can achieve from these motors. So in addition to the stepping performance, another obviously important metric for us is going to be torque that we get out of this motor. And the most important torque number that you'll probably get on a data sheet for a stepper motor is going to be the holding torque. That's the max torque that I can apply to that rotor before breaking that position. So the torque that I can actually apply to drive is typically going to be less than that holding torque, right? That holding torque is the maximum torque that I can sustain when I'm set in a particular position. For that holding torque, clearly I have to have these coils energized. I have to have power applied to my motor. I can also have something called the detent torque, and this is a holding torque when the power is off. And that's due simply to the magnetic attraction between the rotor and the stator poles. So some typical numbers you might find for a particular stepper motor from a data sheet. Your holding torque might be something like 0.23 Newton meters, and that detent torque would be more like 16 millinewton meters, so 0.016 Newton meters in that case. So significantly less, but still not nothing, right? That's definitely a reasonable torque. My basic model for a two-phase stepper motor that I went through previously looks something like this, where I have the A and the A prime coils in series together and the B prime coils in series together. And when I run a current through in this direction, for example, I can set up a particular polar magnetic poles on my stator coils or my stator poles. If I run a current through in a different direction, like this, I can set up the opposite magnetic poles. So this particular configuration, and there are a lot of different winding configurations for stepper motors, but this is probably the most common, is called the monofilar configuration or monofilar winding. And a key point, if I'm thinking about how I'm going to drive these stepper motors, is that I need to be able to reverse my current direction. And these are going to require a fair amount of current, so typically more current than a typical digital logic system can source, or a typical microcontroller can source. So a great solution to this, of course, is H-bridge circuits. Of course, we'll need a full H-bridge for each phase, so the driving complexity and the circuitry required to drive stepper motors can be a little more complex than a basic DC motor. So here's our two H-bridge setup to drive this two-phase stepper motor. In this case, I have a full bridge on this side. Each of these is a half bridge effectively, and another full bridge on the other side to drive the B and B prime coils. And I've labeled these transistors Q1 through Q8. I'm typically going to operate, for example, Q1 and Q4 together. So if Q1 and Q4 are both on, I'll get current going in one direction through here. If Q3 and QT are on, I'll get current going the other direction through here. And same on the other side, Q5 and Q8 are going to work together, and Q6 and Q7 are going to work together. So if I go through the steps that I went through previously to drive this two-phase stepper motor through the 4 steps that it's going to take, I'm going to start by driving current in this direction through my A and A prime coils. And to do that, I'm going to turn on Q1 and Q4 and effectively turn off everything else. Okay, the next step was to turn off current going through the A coils and turn on current going through the B coils in this particular direction. And so in that case, I want Q5 and Q8 to be on, and everything else should be off. Right, then I'm going to reverse my direction. So now I'm going to go back in this direction through the A and A prime coils. And to do that, I'm going to go from this V motor down here through Q3, through Q2 to ground. So Q2 and Q3 are both going to be on in this case for this third step, and everything else will be off. And then finally, I want current going through the B coils in this case. So Q7 and Q6 are going to be on, and everything else will be off. And then, of course, I'm going to repeat. I'm going to go back to step 1, turn on Q1, Q4, turn everything off. Right? So this would allow me to get through all of those steps. Obviously, if you have more phases, more poles, I'm going to take a lot more combinations of these in order to drive my motor around.